So do you have any questions in the break before we continue? So basically what I'm doing is I have my system, my particle is confined within some specific volume, and there is no force acting on my particle within this volume. There is a magnetic field that is going through a region bounded by my volume but not passing through my volume. Now the thing is, if you have such a magnetic field, although the magnetic field is zero in my volume, the vector potential will not be zero. And that it will make the whole difference. So let's see. And now I have this problem which we can solve, and I will be looking for the energy eigenvalues of this problem. So classically, none of the physical properties of my system should be influenced by this magnetic field. But now we will try to see if it is true for the energy eigenvalues. Any questions? Now I have also determined my strategy. So this is my Schrödinger equation is now, let me just copy this. Yeah, here I have a minus sign. My Schrödinger equation is minus h bar squared over 2m acting on psi should be e psi. This is my eigenvalue equation. And just using, now here I had my ansatz for the solution. I will just substitute this into my Schrödinger equation and divide by psi everywhere. So E should be equal to minus h bar squared over 2m 1 over rho d by d rho times r prime 1 over r plus 1 over rho squared phi prime minus I over h bar q phi b over 2 pi c times phi squared, no, sorry, this is wrong, d over d phi minus I over h bar q phi b over c times 2 pi acting on my function phi divided by my function phi, and I have plus z double prime over z. Again, this is my Schrödinger equation within my separation of variable ansatz. Now, since all of these functions r, phi, and z depend only on a single variable, all my partial derivatives just became ordinary derivatives. Well, let's see. If you look at this term only depends on z. And this equation should be satisfied for all values of rho, phi, and z. Keeping rho and phi, I can just change phi, if you like. And this I can change z. And whatever value of z takes, this equation doesn't change. But the first line doesn't change as I change, if I keep rho and phi fixed. As I change z, the first line doesn't change. So the second line also, although it can depend on z, it also should not change. So it should be just a constant. So I will just say z double prime over z should be some constant. Now the thing is this constant positive or negative? Because depending on whether that constant is positive or negative, my function z will behave differently. You see, if it is positive, then z is just kind of an exponential function. But I want z to repeat itself. It should be 0 when the z coordinate is 0, but it should also be 0 when the z coordinate is rho. but exponential function never repeats itself. So it can take the value 0 only once, not twice. So that constant has to be negative. Since at 2 points, at 2 values of the coordinate z, the function z should take the value 0. The exponential function does not satisfy that condition. So that constant should be negative, and I will just call that constant minus k squared. Well, this tells me that z, the function z is just some coefficient times sine of k times z. I don't take the cosine because I have used one of the boundary conditions. When the z coordinate is 0, if you look at the top of the screen, when the z coordinate is 0, the function z should be 0. The cosine does not satisfy that condition. I have the other condition that when z coordinate is equal to h, the function z should also be 0. But that tells me that k times h should be equal to n times pi. N being 1, 2, 3, etc. So for each possible value of n, I have one solution of z. I will call kn to be n times pi over h, and the solution zn, this will be just a times, it can also depend on n, the coefficient sine of kn times z. This is the z dependence of my eigenfunctions. Now let us go back. This z double dot over z is now nothing but minus kn squared. So let me rewrite that equation. E minus h bar squared kn squared over 2m. It's just a constant, so I just move it to the left-hand side. This should be equal to minus h bar squared over 2m, 1 over r, 1 over rho, d by d rho, rho times r prime, minus h bar squared over 2m times 1 over rho squared, 1 over the function phi, d by d phi minus I over h bar q phi b over 2 pi c squared, acting on the function phi. That is h bar. H bar squared. You see, the momentum is h bar k. Just like the free particle. Well, this kn is kind of the z component of the momentum of the free particle, in a sense. But that is kn. You see, I said that here. Where is it? Kn is n pi over h. Yes, this is n pi over h, not h bar. But this over here is h bar squared. That h bar squared is this h bar squared. Now again, if you look at this curly braces, the expression over there depends only on the coordinate phi. And in this equation, that is the only combination that depends on phi. It doesn't depend on rho. So as I change phi, keeping rho fixed, that curly braces also should not change. That basically tells me that that combination over there should also be a constant. So 1 over phi d over d phi minus I over h bar q times phi b divided by 2 pi c squared acting on phi should be a constant. Again, the question is this constant positive or negative? Now, we will basically use the same reasoning. If that constant is positive, then the function phi will be some kind of an exponential, but I want this function phi to repeat itself. Because you see, I'm looking for a function that is single valued. But the phi coordinate, the point, for a given point, let's say the phi is equal to 0, phi coordinate being 0 is the same thing as phi coordinate as being 2 pi, which is the same point as the phi coordinate as being 4 pi. So this function phi should be repeating itself, which basically tells me that that constant should be negative. And let us call that function, that negative constant, minus m squared. Now you can open up that square if you like, but you see this will be just a differential equation with constant coefficients. The solutions will be kind of an exponential function, either oscillatory or increasing, decreasing. Let me look for a function phi of phi is equal to some b times e to power I alpha of phi. Or let me put m of phi. As I said, m should be, my wave function should be single valued, so m should be an integer. 0 plus minus 1 plus minus 2 plus minus 3, etc. Also keep note that here I allow m to take both positive and negative values. Whereas in my solution for z, that n only takes positive integers. The reason is that if you take, for example, n is equal to minus 2, it's just k is changing its sign. If you let k to change its sign, I basically obtain the same function. Sine of minus kz is equal to sine of kz with a minus sign. So it's exactly the same function. So the negative values of n doesn't give me a new function. It's basically the same function. Whereas here, negative values of m just gives me a different function. So that's why I have to allow for both positive and negative values of m. So if you just put it over there, this minus m squared will be 1 over b e to power I m phi. Now every phi derivative will just bring a factor of I times m. So I can replace the phi derivative with I times m minus, let me call this n. N and m will be different. N is not necessarily an integer. Minus I over h bar q times phi b over 2 pi c squared b times e to power I m phi. Well, these cancels. So n squared is equal to m minus q phi b over 2 pi c h bar squared. This is my n squared. Well, already you see that the energy will be a function of n squared, will depend on n squared and hence on the magnetic field. Well, let's continue. This n is this n. Okay, let me just, okay, it's not the same n with the k. Oops, sorry. Okay, so let me just call this alpha. Okay. A better notation. Okay, so what we had this equation. I have now E minus h bar squared kn squared over 2m. This should be equal to minus h bar squared over 2m, 1 over r, 1 over rho, d by d rho, rho times r prime, plus 1 over, no, minus 1 over rho squared times alpha, now this is the equation for R. Alpha squared. You see that curly braces, I called it minus alpha squared. And let me, in fact, call it alpha m. So what's the solution? Let's just try to write it in a form that will be probably more familiar. So let's see, it's 2m 1 over r times 1 over rho. If you take the derivative with respect to rho, you get rho r double dot plus r prime minus 1 over rho squared alpha m squared plus times h bar squared over 2m plus e minus h bar squared kn squared over 2m let me multiply with this r. This is equal to 0. Or r double prime. Let me multiply everywhere with r rho squared. Rho squared r double prime minus plus e minus h bar squared kn squared over 2m rho squared r minus alpha m squared h bar squared over 2m m over h bar squared minus alpha m squared r, this is equal to 0. Right? There is also the r prime plus rho of r prime. So this is my equation. Anyway, the solutions, you can just look it up. It will be Bessel functions, as you pointed out. But the crucial point is the energy values. The energy eigenvalues will depend on this alpha m, which depends on the magnetic field. Which the particle, by the way, never feels. So you see, on one hand, we have this system in which the particle never enters, not even tunnels through a region where there is a non-zero magnetic field. On one hand, on the other hand, we see that the particle, although it never goes through the region where there is a magnetic field, it still feels the effects of the magnetic field because the energy levels will be shifted. The energy eigenvalues will depend on the magnetic field. Mainly because it will feel the effect of the vector potential. Because although the magnetic field is 0, the vector potential is not zero. Any questions? Now let's see. Okay, this is the case when we have, for example, what we did. Okay, our Hamiltonian was P minus Q over C A squared 1 over 2m. This is our Hamiltonian. So the Schrödinger equation just took this form. Well, we said that A can be changing. A is not unique. There are infinitely many A's that correspond to the same magnetic field with zero electric field. So we said that A, instead of A, we can just use A prime, which will be just A plus the gradient of lambda. So H just becomes some other H prime. The Hamiltonian is modified. Here we have some wave functions. They will also be modified. The eigenfunctions, let's say. They will also be different. But since the vector potentials are somehow related, how will the wave functions be related? Now let's check one thing. Yes, I will claim that psi prime, well, it should be unitary just because for every solution I want in one gauge, there should be some corresponding solution in the other gauge. Furthermore, the relation between the two should conserve the probabilities, and even some of the matrix elements should be conserved. It should be invariant. So it will be a unitary transformation connecting the two. So let me just say that psi e prime at the point r will be just u at the point r times psi e. What is this u? That is what I will be looking for. Of course, this u, you say, can depend on r. It's not just an ordinary unitary transformation, it's a unitary transformation that depends on position. Now, what I will claim is that what I would like to have is minus I h bar times the gradient minus a psi prime of r, psi of r. If I make a gauge transformation, this will be minus I h bar, the gradient minus a prime, psi prime of r. This will be after the transformation. And I will ask this to be equal to u of r minus I h bar, the gradient minus a of psi of r. This is what I want. Because once this is satisfied, is h prime psi of e prime, which is 1 over 2m minus I h bar, the gradient minus a prime squared psi prime of r. This is 1 over 2m minus I h bar, gradient minus q over c. A prime times minus I h bar, the gradient minus q over c, a prime psi prime, 1 over 2m minus I h bar, the gradient minus q over c, a prime, u q over c, a psi, assuming that this condition is satisfied, I can just use this one. But you see, basically what I'm asking for if I change the position of u and this minus I h bar gradient minus a prime, when I exchange their position, a prime just becomes a. That is what I'm asking for. Now first, what I would like to show here is that if that is satisfied, then I know, if that is satisfied, I know how to map psi e to psi e prime, the energy eigenvalues will be still the same, etc. Now this is a prime, which will be equal to 1 over 2m u minus I h bar gradient minus a. I just exchange the position of u and the operator on the left. That would just give me, if there is such an operator u, of course, I'm still assuming that there is such a unitary operator u. If that is satisfied, then if I just change their position, a prime just becomes a. Psi. But this is nothing but h of psi e. H of psi, let's say. But h of psi is just e of psi. This is e times psi prime. So what did I do? Okay, on one hand, we already looked at a case where explicitly although the magnetic field is non-zero due to the non-zero vector potential, the observable properties can be modified. That is one thing. That is, well, kind of interesting, but also open to problems, because the vector potential is not unique. We have infinitely many possible choices of vector potentials. We have to make sure that the outcome, our predictions, should be independent of which vector potential we choose. Now, vector potentials are, what are the observables? Like the energy eigenvalues. So if we choose one vector potential, we get one spectrum. If we change a different vector potential, we should still get exactly the same spectrum, not a different spectrum. So which kind of tells me that if I solve my Hamiltonian in a given gauge, with a given choice of vector potential, obtain the spectrum, if I make a gauge transformation, which basically means choosing a different energy, different vector potential, if I choose a different vector potential, I should still get exactly the same energy eigenvalues. But that also kind of indirectly implies that there should be some kind of a mapping between the wave functions I have in one choice of the vector potential and the wave functions I have in the other choice of the vector potential. And that relation should have this form. And furthermore, it should satisfy this condition. That this should be equal to u minus I h bar gradient minus a. Of course, this u, by the way, although I didn't write it explicitly, it can depend on lambda. So this is the condition that u should satisfy. If u satisfies this condition, then I am sure that I get the same spectrum. I know how to map one set of wave eigenfunctions to the other set of eigenfunctions. And again, keep in mind that this gradient operator over here is acting on anything on its right. Not just u, but if when the wave function comes after u, it will also be acting on that. So let's try to find what this u should be. This is the condition that I need to solve. Now keep in mind a prime is equal to a plus the gradient of lambda. Now let me expand the left-hand side. Now the gradient of u of lambda, I can write this in this form. U of lambda times the gradient plus the gradient of u of lambda. I put it in parentheses to imply that that gradient in parentheses only acts on u, not on what comes afterwards. This is just a chain rule. Just imagine we have some function psi over here. Not the chain rule, the product rule. I'm just taking the derivative of the product of two functions. So gradient of u of lambda, I will write as u of lambda times the gradient plus the gradient of u itself. Let me just substitute it in my first line. Minus I h bar u of lambda times the gradient minus I h bar the gradient of u of lambda. And keep in mind, I have this derivative because I'm assuming that u might depend on the position. If u doesn't depend on the position, its position derivative would have been 0. Minus, well, a prime is a u of lambda plus gradient of lambda u of lambda. This is my left-hand side. On the right-hand side, I have minus I h bar u of lambda gradient minus u of lambda times a. Now, u of lambda is just a function of the position, or an operator of the position operator, a function of the position operator. Similarly, a, at least in the problem that we are considering, a is just a function of the position operator. So u lambda and a, basically they commute. So a times u lambda on the left-hand side cancels u lambda times a on the right-hand side. This is first cancellation. I have u lambda times the gradients. They are common on the left-hand side and also on the right-hand side. So this tells me that minus I h bar gradient of u lambda is equal to gradient of lambda times u lambda.
O lambda nereden geldi?
Which lambda?
En son yazdığımız gradient lambda. Üstte yazdığımız gibi.
This one.
Evet.
It is this one. It's my gauge transformation.
Pardon yani.
You see, I just substitute a prime with its definition in terms of a and lambda. But this basically tells me that u of lambda is just h power I over h bar times lambda. If I take the gradient of u of lambda, it just brings an I over h bar. If you multiply with minus I h bar, it just gives 1. It also brings the gradient of lambda. So basically now I'm kind of redefining my gauge transformation. Not redefining, I'm extending my gauge transformation to include the wave function. You see, we started with defining the gauge transformation as something we have in electromagnetism for the scalar and the vector potentials. Now here, we are just considering the case where we have the scalar potential is 0, A is transformed as with the gradient of some lambda, and now we know that the wave function should also be transformed through this operator, where lambda is the same lambda. These two lambdas are equal. And I know that the energy eigenvalues are the same, independent of my gauge transformations. So-called energy eigenvalues are gauge invariant. They do not change with gauge transformations. My wave function is not gauge invariant. It changes with gauge transformations. Magnetic field is gauge invariant. It doesn't change under gauge transformations, but my vector potential is not gauge invariant because it is changing with gauge transformations. What about the momentum? Let's see the P. Under a gauge transform, which we defined as, let's say, psi star minus I h bar, the gradient acting on psi. In terms of wave function, this is how we define the expectation value of P in a wave in any wave function. Well, this will be equal to d cubed r. Well, not equal to. Under a gauge transformation, this just becomes psi star is just psi star e to the power minus I over h bar lambda minus I h bar, the gradient of e to the power I over h bar lambda psi. This is equal to d cubed r psi star e to the power minus I over h bar lambda. Well, if you take the gradient, you get a gradient of lambda now let me write it in a slightly different form. E to the power I over h bar lambda, gradient of lambda minus I h bar, the gradient of psi, multiplying psi. Well, these will cancel. And I have the expectation value of the canonical momentum is equal to gradient of lambda, now the average of the gradient of lambda, minus, now plus the average of P. So you see, P changes. Well, let me just make a slight correction to be more formally correct. This A over here has Q over C. So it basically, this has Q over C, this has Q over C. So this also has Q over C. Here I have Q over C, Q over C. This is my U. So here I have Q over C, factors of Q over C. Q over C. So the expectation value of canonical momentum itself is also not gauge invariant. Let's look at the kinetic momentum. Remember, kinetic momentum we had defined as P plus Q over CA. Or minus Q over CA, sorry. Now the expectation value of kinetic momentum, which is the expectation value of P minus Q over C times the expectation value of A. Then we make a gauge transformation. We already know how P transforms. It is the gradient of A, gradient of lambda times Q over C plus the expectation value of P. This is what the expectation value of P becomes under a gauge transformation, minus Q over C. Well, the expectation value of A becomes just the expectation value of A plus the gradient of lambda, expectation of gradient of lambda. And this term basically cancels this term. What remains is we have the expectation value of P minus Q over C A. but which is nothing but the expectation value of the kinetic momentum. So expectation value of the kinetic momentum does not change. This kinetic momentum is the momentum that you can identify as the mass times the velocity. You see the kinetic momentum. In Heisenberg picture, we had seen that it is m times dx by dr by dt. So you see, physically observable quantities like the kinetic momentum, they are still gauge invariant, as they should be. X is gauge invariant. Position is gauge invariant. It doesn't change if you change the gauge, but the canonical momentum is not gauge invariant. Vector potential is not gauge invariant. Its expectation values changes if you change your gauge. Now, what else did we study? Which other properties did we look at before? You see, we have this weird situation that kind of the wave function and the energy eigenvalues, they depend on the vector potentials we have. But we know that the vector potential is not unique. There are infinitely many vector potentials. So at least the physically observable properties, they might depend on the vector potential, but they should not depend on the choice of the vector potential. That's kind of what we are looking at over here. We already seen one case where the energy eigenvalues depends on the vector potential, but now we see general proofs that the energy eigenvalues, although they might depend on the vector potential, they do not depend on the particular choice of the vector potential. You see, in this problem over here that we discussed, now this is just one possible choice of the vector potential corresponding to this problem. There are infinitely many other vector potentials that would correspond to the same problem. But the proofs that we are doing over here, first the proof that the energy is independent of the vector potential, energy spectrum, this tells me that if I had chosen some other vector potential for my initial problem, well, no problem, the energy eigenvalues will still be the same. And here we show that, okay, the canonical momentum, it's not gauge invariant, it depends on the gauge, but that basically tells us that it is not something we can directly observe. It is the kinetic momentum that is gauge invariant, and hence we can observe it. This kinetic momentum will be independent of which gauge we choose. Let's look at the probability densities and the probability current. You see, if you remember, we had talked about the probability density to be psi star psi square root. Well, it is obvious that this is gauge invariant. You see, under a gauge transformation, this just becomes psi star u dagger u psi. U being this exponential involving the lambda. But u dagger u is just 1. So this is psi star psi. So rho of r is gauge invariant. Well, we had identified the probability current before. Well, in our previous case, if you remember the expression, well, let's say it was proportional to the imaginary part of psi star gradient of psi, which you see is not gauge invariant. Well, there is a catch over here. This result that we obtained before doesn't hold in this case. Is because when we were driving this result, we had assumed that J of R, this is valid only if H is equal to P squared over 2M plus V of R. We derived it in this case. Now, our potential now, H is P minus Q over C A squared over 2M. So that won't hold anymore. That won't be valid anymore, that expression. Well, let's try to derive what J should be in the presence of the magnetic field. This J, remember we said that J satisfies this equation, del rho by del T plus the gradient of J. Divergence of J should be equal to 0. So we said that, okay, rho is kind of, if you make an analogy with kind of fluid dynamics, something fluid, rho is the probability density or the density of the fluid. And with time, this probability density will be evolving in time. And as this probability density is evolving in time, the total being constant, it just means that the probability that the particle will be found in one part of space will just flow to the other parts. And that flow of probability is what we call the J. Well, I will not repeat the derivation. You can just repeat the derivation. Basically, J of R will be the imaginary part of psi star, proportional to, let's say, times P gradient minus I over H bar over I, Q over C A. Psi. Well, basically, you see, to go from one Hamiltonian, P squared over 2M plus V of R, to go to the other Hamiltonian, P minus Q over C A, squared over 2M plus V of R. What you do is you just replace P by P minus Q over C A, or the gradient operator by gradient minus I over H bar Q over C A. That is what I did over here. So it's basically the same expression plus that additional term. Again, the gradient part is gauge dependent. The vector potential part in that expression is gauge dependent, but the two gauge dependence basically cancel each other. Now let's do one more thing before you go, if we have time. No, we don't have. Now, any questions? Which one? Well, we are using kind of the, which one? This one? Well, I mean, Ehrenfest's theorem is a general theorem, not necessarily restricted to gauge transformations. So it basically states that the classical quantities are valid in quantum mechanics in the form of expectation values. So this is our Ehrenfest theorem in this case is that pi is equal to dx by dt. Well, expectation value of position should be gauge invariant. It should not depend on our choice of gauge. So should the expectation value of the kinetic momentum, which we call the pi. And we had actually shown that the expectation value of this kinetic momentum is also gauge invariant. It doesn't depend on our choice of gauge. Okay, so see you on Wednesday.